Hi, this is section 4.1, inverse functions. So function f with domain D and range R is called a one-to-one function. If either of these two conditions is true, we're going to go with the second one. It's a little bit easier to show. So we're going to go with part B, this definition. So whenever f of A is equal to f of B in the range, then that means that A has to equal B in the range. If that's true, then we have a one-to-one function. So let's apply that to this first problem. So let's say if f of A equals f of B, then we have, on the left side, we substitute A into x, and we get 2A plus 5. On the right side, we're going to plug in B into x, and we're going to have 2B plus 5. Now we got to see if we can reach the conclusion that A has to equal B. Well, we can subtract 5 from both sides. That's going to give us 2A equals 2B. Then we would divide both sides by 2, and that would give us our conclusion, A equals B. Therefore, ... those three dots in a triangle mean therefore F is 1, 2, 1. All right, let's try the second problem. Let's do the same thing. If f of A equals f of B, then we have on the left side A squared minus 5. On the right side we have B squared minus 5. Let's add 5 to both sides. Now we have A squared equals B squared. In order to get rid of the square, we square root both sides. That's going to cancel out the squares. And now we're going to have, whenever you take the square root of both sides of an equation, that introduces a plus minus. So we have A equals plus or minus B. So in this case, we don't necessarily have A equal to B. We have A equal to positive B, or we have A equal to negative B. So therefore, this one is not 1, 2, 1. So that's how you would show that a function is one-to-one, or also you can show that a function is not one-to-one, as we just did right now. All right, the next page shows us the horizontal line test. So first thing we should do is test a function to see if it's a function, first of all, by using the vertical line test. So you can draw a vertical line. If it only crosses one time, that means it is a function. If it intersects twice, it's not a function. If you have a function, then you can check to see if it's a one-to-one function by using a horizontal line test. So you draw a horizontal line, and the same rule applies. If it intersects more than one time, then it is not one-to-one. So let's find out whether these graphs represent functions or one-to-one functions or not. So the first graph, we're going to draw a vertical line to see if it's a function. As you can see, it only intersects once. That means it is a function. Now if we draw a horizontal line, you'll see that it intersects twice. So therefore, it is not one-to-one. So it is a function, but it's not a 1-to-1 function. The next graph, if you draw a vertical line, you'll see that it's not even a function. It fails the test to determine whether it's a function or not. So this is not even a function, not a function. So if it's not a function, then you can't really test to see if it's a one-to-one function, because the prerequisite of being a one-to-one function is you first have to be a function. Same goes with this third graph. It intersects twice, so therefore it's not a function. Not a function. All right, so the theorem on inverse functions. So let f be a one-to-one function, and the domain is D and the range is R, and function g is the inverse of f if and only if both of these conditions hold. So we got to show that the composition of g of f of x is equal to x, and vice versa. We have to show that the composition of f of g of y is equal to y. You don't have to use y. You can also use x for both of them. Like I prefer to use x for both of them. So I'm going to go ahead and do that. So we're given two functions here, f and g. And we need to use the theorem on inverse functions to prove that these functions are inverses of each other. So in other words, we got to find the composition and show that it's equal to x in both directions. All right, so first let's start off with g of f of x. So for that, I'm going to substitute the f function into the g function. So that means we have the square root of x squared plus 5, that replaces the x here, minus 5. Well, notice the parentheses don't really make a difference, so we can get rid of the parentheses. And when you do that, you'll see that the 5's cancel each other out. And then we have the square root of x squared. The square and the square root cancel out, which leaves us with just x. And that's exactly what we're trying to achieve. So now we got to do the other direction now. So now we're going to do f of g of x. You could do y if you prefer y, but I just prefer x. So now we're going to reverse the direction. This time we're going to substitute the g function into the f function. So it's going to be the square root of x minus 5 to the second power plus 5. The second power comes from this exponent up here, and the plus 5 comes from here. X gets replaced with the entire g function. And now we can cancel the square and the square root, which gives us x minus 5 plus 5. 5's cancel. We're left with x. So therefore, f and g are inverses of each other. Great. All right, so now the next theorem says that the domain and range of f and f inverse. So what they're saying here is that the domain of the inverse function is equal to the range of the f function, and also the range of the inverse function is equal to the domain of the function. So here we have a function. They want us to find the domain and the range of the inverse without even finding the inverse. So we're going to apply this theorem up here. So what you want to do is think of asymptotes. This is a rational expression. Let's look at the vertical asymptotes. So if you recall, the vertical asymptote is when you set the denominator equal to 0 and you solve. So x cannot equal -3, because if x is equal to -3, then you're dividing by 0, which is undefined. So our vertical asymptote would be x equal to -3. So the domain would be all the values that are between, so the domain of f would be all the values from -infinity to -3, union -3 to infinity. Now let's find the range. The range, which is a horizontal asymptote. If you find the horizontal asymptote, that's going to tell you what the range is. So whenever the degree of the denominator is greater than the degree of the numerator, as is the case here, then your horizontal asymptote is automatically y equal to 0. All right, that means that the range is going to be range of f will be all the values from -infinity to 0, union 0 to infinity. All right, so that's the domain and the range of the function, but we want the domain and the range of the inverse function. So let's write that in in red. Domain of f inverse is going to be the range of the function. As you can tell, the domain of the inverse is equal to the range of the function. So this is going to be the domain of the inverse. And the range of the inverse is going to be the domain of the function. So there we have it. -infinity to -3, union -3 to infinity. So once again, to find the domain of the function, you find the vertical asymptote, which is -3, and then you exclude that value from the domain. And then to find the range of the function, you find the horizontal asymptote, and you exclude that value from the range, and then you just swap, and that's how you get the domain of the inverse and the range of the inverse. All right, now we're going to actually find inverse functions. It's a 4-step process. Step number 1 is to replace the function notation with y. Step number 2 is to exchange x and y. Step number 3 is to solve for y. And then the final step is to replace y with this notation, inverse notation. So let's go through those 4 steps. Step number 1, I'll call that S1, is to change the f of x to y. Step number 2, interchange x with y and y with x. So there we go. I switched out the y with the x and the x with the y. Step 3, this is where we solve for y. So to solve for y, we have to subtract 7. So now we have negative 2y equals x minus 7. And then we divide by negative 2. So we end up with y equals x minus 7 over negative 2. And our final step is to change the notation to f inverse. And that is our final answer. So that's a 4-step process. Let's try another example. This one's a little more challenging because there's 2 x's instead of 1 x, but you'll see what we do here. For step 1, we change the f of x to a y. Step 2, we interchange x's and y's. Oops. Step 3, this is where we need to solve for y. This is where it becomes a little bit more challenging because there's 2 y's, so you have to solve for y, which means we have to group the y's and factor it out. So this is the way you would do it. You would first multiply by the denominator to clear out that fraction. And you might as well distribute because we're going to have to do that anyway. So 2xy minus 5x equals 3y plus 2. So what I said earlier was that we need to group the y's, get them on the same side in order to factor out the y. So let's move the 5x over to the right side and the 3y over to the left side. So plus 5x to both sides, minus 3y to both sides, and that will give us 2xy minus 3y equals 5x plus 2. So now we're in a position where we can actually factor out the y. So factor out the y, and we're left with 2x minus 3 equals 5x plus 2. And to solve, we're going to divide both sides by 2x minus 3. And that's going to do it. So now we're off to step 4, which is to change the notation to f inverse. And our final answer is 5x plus 2 over 2x minus 3. Okay, the last problem is a graphing problem. So we need to take this function, we need to find the inverse of it. Then we need to sketch both the function itself and the inverse on the same coordinate plane. So let's do this. You can create an XY table if you'd like. All right, let's go with -3, -2. Actually, I'm going to pick values that are perfect squares. So if I go with -3, that's going to be 0, right? If you plug in -3 here, -3 plus 3 is 0. Let's pick -2 because -2 plus 3 is 1, and the square root of 1 is 1. All right, the next perfect square is 4, so I want to make this a 4. So that means I'm going to choose 1 for x, because 1 plus 3 is 4, and the square root of 4 is 2. I'm going to choose one more value. The next perfect square would be, actually that's good enough. We can leave it at that. -3, 0, -2, 1, and 1, 2. So our square root function is going to look like that. All right, now we need to find the inverse. So let's go through the 4-step process. Step 1 is to change f of x to y. Step 2 is to interchange x and y. Step 3 is to solve for y. So I'm going to square both sides in order to get rid of the square root. So x squared equals y plus 3. Subtract 3. And we've solved for y. And then finally change the notation to f inverse. So we found the inverse function. Now we can do the same thing. So if you notice, this is a parabola shifted down 3 units. We're going to learn transformations later in this class. But it's going to be 1, 2, 3, shifted down 3 units from the vertex. So it's going to look like that, but if you notice, it's not a one-to-one function, and only one-to-one functions have inverses. So what we have to do is we have to define this only when x is greater than 0. So it's basically half a parabola. So this is only going to work when x is greater than or equal to 0. So instead of having a full parabola shifted down 3 units, we're only going to have half a parabola, the positive side. So let's go ahead and graph that. So you can create another xy table. I'll call it x f inverse x. So let's see, when x is 0, y is negative 3. When x is 1, you get 1 squared minus 3 is negative 2. When x is 2, you get 2 squared is 4. 4 take away 3 is 1. All right, that should be good enough. I should have used red. That's okay. I'm going to use red now. So let's graph these 3 points, 0, negative 3. As you can see, it's shifted down 3 units. 1, negative 2, and 2, 1. If you graph those, you will see that's the inverse function. And look it up here. Compare these 2 tables. What do you notice about the x and y coordinates? They're interchanged. 1, negative 2. Negative 2, 1, 2, 1, 1, 2. So that's basically the second step of finding inverses. You're interchanging x and y. So that's what's happening. These coordinates are getting interchanged, and that's how you graph inverses. So we didn't even have to go through this process. You could have just reversed these, and graphed that, and that's how you would have gotten your coordinates. And notice that that is a reflection of the y equals x line. And that's always going to happen. Whenever you graph 2 inverse functions, you're always going to get a reflection over the y equals x line. And that concludes this section.